Have you ever watched a great athlete make a brilliant split-second play, only to see them completely freeze up just moments later? Well, it's not about skill, and it's definitely not about luck. It's all about how their brain is routing what they see. In this ARES lesson, we're diving deep into the two parallel streams that assign meaning to everything you see, and how that process dictates performance under pressure.
Okay, so here's our game plan. We're going to start by looking at two performance failures that seem like total opposites. Then we'll unpack the two-stream model of vision and figure out how the specific task at hand determines which stream gets to be the boss. From there, we'll revisit those failures with this new lens, and finally, we'll see how this all fits back into the bigger ARES performance loop. Let's jump in.
All right, let's kick things off with a couple of scenarios you've probably seen a million times. On the surface, they look like polar opposites: indecision on one hand and pure recklessness on the other.
You know what I'm talking about, right? You see an athlete in a huge moment, and they just hesitate. They seem to be reading the play perfectly, but they act a split second too late. And then, maybe the very next possession, that same person is all instinct, bam! They commit instantly, but they commit to the wrong thing. They totally bite on a fake. So what is actually going on here?
This breaks it down perfectly. On one side, you've got the thinker. This is the athlete who gets caught in analysis paralysis. They're processing everything, but they fail to act in time. And on the other side, the reactor. All action, no context. They jump on the first thing they see, like a head fake or a feint. Now, these look like completely different problems, don't they? One is thinking too much, the other isn't thinking enough. But what if they're actually two sides of the same coin?
And here is the absolute game changer. These are not opposite problems, and they're not failures of vision or skill or athleticism. They are both symptoms of the exact same issue, a routing problem. It all comes down to how visual information is being sorted and assigned meaning inside the brain.
Okay, so let's get into the mechanics of how the brain actually pulls this off. We're about to see that meaning isn't assigned down some single superhighway. It happens in parallel through two highly specialized streams.
So where does all this magic happen? Right here, in the root phase of the ARES performance loop. This is the critical handoff that happens right after you acquire the visual information and just before you go to execute an action. And trust me, what happens here in the root phase determines the quality of everything that follows.
So once visual information comes in, it doesn't just go down one pipe. It immediately splits and travels along two different pathways at the exact same time. First, you have the dorsal stream. You can think of this as the where or how pathway. It's the action stream. It's obsessed with spatial location, guiding your movement and helping you interact with things. In parallel, you've got the ventral stream. This is your what pathway. This is the identification stream. Its job is to recognize objects, spot patterns, and figure out what stuff means.
And this is absolutely essential to understand. Both of these streams are working with the exact same raw data from your eyes. It's not like one gets a clearer picture. They are simply optimized to answer different questions, at the same time using the same input. Dorsal solves for action. Ventral solves for identity.
Okay, so if both streams are always on and working in parallel, who's in charge? Well, it turns out the task itself gets to decide which stream takes the lead. The environment is literally pulling for a specific kind of solution.
So at a baseline, just looking around the room right now, both streams are active. They're processing the visual input side by side, each doing its own job. They're working together, complementing each other, not competing.
But now, let's introduce a time-critical task. Think about a batter trying to hit a 100-mile-per-hour fastball, or a goalie facing a one-timer in hockey. In these moments, there is absolutely zero tolerance for delay. The number one priority is immediate, targeted action. And in that fraction of a second, the system biases its processing. The dorsal stream becomes dominant. The where is it going, and how do I intercept it information gets top priority to guide a super-fast, accurate motor response. The what stream is still running in the background, but its input isn't driving the immediate action.
Now let's flip that scenario completely. Imagine a quarterback trying to read a disguised blitz, or a poker player trying to spot a bluff. The priority here isn't just reacting to movement. It's about identifying a pattern, connecting it to past experiences, and figuring out the meaning behind what the opponent is showing you.
In this case, the ventral stream takes over. The what pathway becomes dominant because it has to provide context and identification. A purely reflexive, dorsal-driven action would be a huge mistake. The system has to know what it's seeing before it can decide how to respond.
And this leads us to what is probably the most important rule in this entire lesson. This is not a conscious choice. An athlete doesn't sit there and think, I think I'll use my ventral stream now. No way. The demands of the environment, of the task itself, automatically pull for the right processing priority.
So now, with this new framework, we can go all the way back to our two athletes at the beginning, the thinker and the reactor. And we can finally understand their failures, not as a lack of ability, but as a simple mismatch in stream dominance.
Our hesitant athlete, the thinker, is dealing with ventral over-reliance. The task is screaming for a fast, dorsal stream solution, where's the puck going, but their system is stuck prioritizing the ventral stream, asking what kind of formation are they in. That's what leads to that fatal hesitation. On the flip side, the reactor is a classic case of dorsal over-reliance. The task demands a ventral interpretation. Is that a real move or a fake? But their system just defaults to a pure reflexive action, which makes them incredibly easy to fool.
So, it all boils down to this. In these moments, performance failure isn't about having bad eyesight or not getting enough information. It's about the brain prioritizing the wrong kind of meaning for the job at hand. It is, at its core, a routing error.
All right. Let's wrap this up by zooming out and seeing how this critical routing decision impacts the entire ARS performance loop, because it definitely doesn't happen in a bubble. The decision on stream dominance that happens in the route phase is hugely influenced by the quality of the signal it gets from the acquire phase. But just as important, the execute phase inherits whatever bias comes out of route. Look, you can't execute a fast, fluid, reactive movement if the information was routed for slow, careful analysis. And you can't execute a smart, adaptive play if the information was routed for pure reflex. Your execution is simply a reflection of the routing that came before it. So, as we close this out, let's make sure these key takeaways are locked in. Number 1, dorsal and ventral streams are not enemies. They are parallel solutions to different problems. Number 2, a lot of common errors in performance are just mismatches between the task's demands and which stream takes control. And finally, number 3, it's the environment, the task itself, that determines the routing priority, not the athlete. Getting this parallel routing architecture is the absolute foundation for what comes next in the system. Because even after visual information gets routed down the correct stream and assigned the right kind of meaning, that signal still has to pass through a series of checks and balances in the prefrontal cortex before it gets the green light for the execute phase. And that constraint is what we'll cover in our next lesson.